So we are going to continue 2.3, the limit laws. We left off on this example, so let's jump right in and see what the heck is happening. Now, we have explored that little notation where the little plus beside it means that we're coming in from the right and the little minus coming in from the left. There are some functions that work perfectly from one direction but not another. And a perfect example of that is our square root function. So let's first explore what the graph looks like, and let's look at what we could do algebraically to kind of verify what the heck's happening. If you look at the function, the square root of x minus 3, we should recognize quickly, hopefully, that that is the square root function moved 3 to the right. So the function looks something like that, okay? So in the first example, or part A, it says, what height are we approaching from the left? Well, if you look, the left value doesn't exist. So this doesn't exist. There's nothing on the left side, so how can we determine what's happening on the left side? There's nothing there. Now, how could we check? Well, a value to the left of 3 is 2.99. So let's plug in 2.99 into our function, and we get negative 0.11. The square root of a negative is an I. So that's I times the square root of 0.11. Limits only work if you get a real number answer. That is not a real number. That is a complex number. So that's another demonstration that doesn't work. Okay. Now, for the second piece, it says, what is the limit as we approach 3 from the right? Well, as we come in from the right here, you can see we are approaching a height of 0. It works perfectly fine. There is no problem. Mathematically, let's check. If we plug in 3.01, we get the square root of 0.01, which is 1/10. Small number close to 0. We're heading to 0. So the algebra should verify what the graph is telling you. Do you need both? No. If you know what the graph is like, you can use the graph to find the limit. If you know what you could possibly check for the algebra, you can do the algebra. Either should verify the same darn thing. If it doesn't verify the same darn thing, either your graph was wrong or the algebra was wrong. But they should mesh together. Any questions about this one? Does that make sense? Okay. Now, limits for a piecewise function can be an issue because there are those boundaries where the two come together. So you might notice that they have checked the boundary value of 2. So if you're taking a limit of any value less than 2, like the limit of 1 as we approach 1, the limit as we approach 0, the limit as we approach -5, you use this function. If it's anything greater than or equal to 2, well, greater than 2, so 3, 7, 9, you would use this function, and it's just a direct substitution. But that border, if they don't come together, can mess you completely up. Now, I want to show you how first algebraically to verify it, and then I want to show you how to graphically, because the graph and the algebra should always go together. As we come in from 2 to the left, that are values that are less than 2. So here we're talking about x's that are less than 2. That is in this top piece. So as we approach values from the left of 2, you just get to use that top piece and you don't have to worry about it. Now, normally I wouldn't plug 2 into that top piece, but I'm approaching and getting almost to what value? Well, if you plug in 2, you get 4 times 2 minus 3, or 8 minus 3. I'm going to a height of 5. Now, I don't land there. There's an open circle there, but a limit doesn't ask me where I land. A limit asks me where do I head? Where am I almost going to land? Now, for things that are greater than 2, that's this notation, that we're coming in from the right. So this is x's that are greater than 2, so that's time we use this part of the function. If we plug 2 into that part of the function, we get 2 minus 3 squared, or negative 1 squared, which is 1. Now let's go back and let's look at the graph for a moment. So, when you're going to graph a piecewise function, put the border on. There's a border at 2. From the left of 2, we're using the line 4x minus 3. So we would start at negative 3, count up 4 over 1, up 4 over 1, and there's an open circle. You'll notice that we are approaching a height of 5. Okay. That's what this says. As we come in from the left, we're approaching a height of 5. Next, let's do this piece. That is a parabola that has its vertex at 3. There's a border at 2. So I would probably plug in 2, 3, and 4, just to get the shape. The vertex is at 3. If you plug in 2, we already did that. We got 1. If we plug in 3, we get 0. If we plug in 4, you also get 1. So it looks something like this. So as we go from the left, we're approaching a height of 5. As we come in from the right, we're approaching the height of 1. Our graph and our first 2 answers match up. Now, this is saying, as we come in from both sides, what is the height? Well, because both sides are not connected, since this algebraic value and this algebraic value are disconnected, we would say that this doesn't exist. It has to be connected. Now, there could be an open circle there, but they still have to be connected, and they aren't connected. So you can see in both aspects, the algebra and the graph match up. So there's example 2.22. Any questions? We good? Makes sense? Okay. Let's look at example 23. Now it says evaluate using the limit laws. Well, if I see an algebraic expression, I'm really not completely positive of what the graph looks like, I will jump right in and try substitution. So you should always just try to substitute the value of 2 and see what you get. Are we getting a value that actually even works? If you plug in 2 from direct substitution, you get 2 minus 3 over 4 minus 4, which is negative 1 over 0. This tells me that I just found a vertical asymptote. So the answer to this, without doing any other math, is either negative infinity or positive infinity. As we approach to that vertical asymptote, you always are going swooping up and skimming across it or swooping down. So the answer right now, I know, is either positive infinity or negative infinity. How do we find which infinity it is? Well, if this little symbol says a negative, I only have to plug in something just to the left of 2. I usually tend to just take away like 100th. So let's plug into our function 1.99. So it's going to be 1.99 minus 3 over 1.99 squared minus 2 times 1.99. Now, all we really are asking for, I know the answer is either positive infinity or negative infinity. So I really am just saying, do I get a big negative answer? Then my answer is negative infinity. If I get a big positive answer, my answer is positive infinity. So it's one or the other. Now, how do we find which? Well, on top, would you agree that 1.99 minus 3 is a negative? So that's easy to establish real quick. Now let's think on the bottom. 1.99 squared minus 2 times 1.99. Wouldn't this value be just a little bit bigger than this value? I mean, just naturally, if you think about it. That's a negative. Now, if you put it into a calculator, you can find the exact number. You know, I don't need the exact number, but if you're unsure, 1.99 squared minus 2 times 1.99 is negative 0.199. Okay. But all you really care about are the signs. A negative over a negative is a positive. So my answer is positive infinity. Now, graphically, we know there's a vertical asymptote. We can check the work using Desmos. So if you put x minus 3 on the top of your fraction, divided by x squared minus 2x on the bottom, I would type in the vertical asymptote that you're approaching, which is at x equals 2, and then scroll and think as we approach it from the left side, what height am I going toward? I'm going to draw since I can't really scroll real good there. I'm going to draw you a little very poor representation. You can see that this piece here is the left side of the asymptote, and it's going up to positive infinity. So however you slice it, the graphical interpretation and the algebra should always match up. If it doesn't match up, you're doing something wrong. The two things have to always go together. So if you get not 0 over 0, because remember that we can manipulate the algebra, but if we get a number over 0, we have found a vertical asymptote. What am I doing? Am I flipping up to that vertical asymptote? Am I flipping down? Now, if you wanted to do the limit as x approaches 2 from the right of this function, the answer is negative infinity because of this end. So that means that the limit as x approaches 2 in general does not exist because one's going up and one's going down. This graph's an interesting one. It has a vertical asymptote at 0 and a vertical asymptote at 2. So it has 2 vertical asymptotes. We could contemplate what the heck's happened. But watch what they're asking. Here, if they're asking from the left, the answer is positive infinity. If they're asking from the right, the answer is negative infinity. If they're asking for 2 in general, it doesn't exist because which one do we pick? If they don't match, we can't pick one. There is no real answer. Okay, so that's 2.23. Any questions about that? Okay. Squeeze theorem. Squeeze theorem is really kind of an interesting theorem. It basically says that if 3 functions are always arranged, so the f is below the g is below the h, And if the limit as we approach A of the outer two functions is L, then the inner function had to be squeezed in there, and it also is equal to L. Now, why is this helpful? This is a helpful theorem. We're not going to use it very often, maybe once or twice, but it's helpful for us to find a limit to a value of a funky, weird function if it's surrounded by two functions we know about. So like the two functions on the outside might be functions where we're allowed to use direct substitution. The function on the inside, it might not work as good, but if we can establish the fact that it's stuck in the middle, then it will be helpful as to, solving. It's usually only used for weird functions. That's when it's used most often. Okay, so let's do an example of the squeeze theorem. That's our last example. Okay. So it says, find the limit as x approaches 0 of x cosine of x using the squeeze theorem. Now, if you try direct substitution, we get 0 times the cosine of 0. And it appears as if, because the cosine of 0 is 1, it seems as if we're going to get 0 times 1 or 0 as an answer. Okay? But I want to show you why we know for sure that the answer is 0. Okay? Because what does x cosine of x look like? That's not a graph that we look at a lot. We know what the graph of x looks like. It's a straight line. It's the identity line. And then the cosine function's a wave. So what does it look like when you put those things together? Okay, so let's think about what we know about the cosine. The cosine is always a value stuck between -1 and +1. That's where the squeeze theorem is going to come into play for the sine function and for the cosine function. So if you are looking for a limit of a sine function and a cosine function, it's a wave. But if we establish right off the bat that it's between +1 and -1, because you remember the wave is always stuck between that height, we can start to possibly use the squeeze theorem. Now, this function is different from this function because it has that x on it. So if you multiply through by x, and when we multiply through by x, here's the problem. We need to multiply through by a positive so things don't flip around. So let's make it an absolute value. And let's think about the limit as x approaches 0 of the negative absolute value of x and the positive absolute value of x. As we approach 0 for the negative absolute value of x, we know that's just an upside down v, hopefully. From both sides, we are approaching a height of 0. This one is a right side up v. As we approach 0 from both sides, we're heading to 0. So since the limit of this one is 0 and the limit of this one is 0, since this is stuck in between it, it's also going to be 0. Now, all we've done so far is know that the limit as x approaches 0 of the absolute value of x of the cosine of x is 0. How does that give us exactly what we want? Well, the absolute value of 0 is 0. And so then we can interpret the fact that this is the same as this. So it's 0. That's the squeeze theorem. I've seen it used a lot for, the one I think I've seen it used more than, this book chose that one, I don't know why. I've seen it used this function. That's a neat one that it comes out kind of cool. You start out with the sine of x, or sine of 1 over x, and then you go from there. You multiply through by x squared, and you still, I think, get 0. So yeah, that's the squeeze theorem. Is kind of interesting. Again, are we going to use it? Not very often. No. Okay. So these are the homework problems. 83 to 123, just the odds. So let's actually jump to the book. And let's take a look at the homework a little bit. Let's get started. So let me pull open the book here. I always think, oh, I should open up the actual page before we start, and I always forget. Okay. So 2.3, again, the assignment were the odds, 83 to 123. So let me highlight those. And then we'll do one from each section. Or whatever time allows. Okay, so let's start here with this first little section, 83 and 85. It says, use the limit laws to evaluate each limit, justify each step by indicating the appropriate limit laws. I don't have any justification, just do it, okay? So for 83 and 85, you always want to try direct substitution and see if we get a value that works. Both of these are going to work using direct substitution. So feel free to just show me that you just plug in 0 for the top one and -2 to the bottom one, and you get an appropriate limit. You can justify it even by looking at the picture, that 0 exists and comes in from both sides and is defined and everything is beautiful. 87, 89, and 91 says use direct substitution, so they're just going to work. 93, 95, and 97, let's look at what it says. It says use direct substitution to show that the limit leads to the indeterminate form 0 over 0, and then evaluate. So remember what I've always said from limits when we started. You should always use direct substitution. If you get a value, it's probably the answer. If you don't get a value, why did you not get a value? If you get 0 over 0, that's what they're talking about here. These ones, you can then manipulate the algebra. Let's talk about each problem individually. For 93, you're going to get 0 over 0. Show me that. And then factor. And then once you factor, you should be able to reduce it and get good things happening. 95, they're both polynomials. Factor. You should be able to reduce and get nice things. 97, that is a square root function, so we have to use the conjugate. So what's the conjugate we're going to use for 97? What's the conjugate we're going to use for 97?
Square root of t plus 3.
The square root of t plus 3. So remember, you're going to put this in parentheses. You're going to multiply top and the bottom by the square root of t plus 3. And magical things will happen from there. So that's what you want to do for that one. For 99 and 101, it says, oh, that's still the same thing. You're going to get 0 over 0, and then you should be able to manipulate the algebra. This one, use what we know about the tangent, that it's sine over cosine, and things should cancel out pretty nicely. 101 is a factorable. So here, use trig. the tangent sine over cosine, and here we're going to factor. So those continue what the same thing they said from before. Now let's read the instructions for 103 and 105. It says, in the following exercises, use direct substitution. Then use the method in example 2.23 to simplify to determine the limit. So let's do 101, 103 together. These ones, you notice we're approaching from the left or the right. So we're probably approaching a vertical asymptote. How do you know that? Well, you use direct substitution as your first step anyway. You should always do that. If I plug in -2, I get 2 times 4, or 8, minus 14 minus 4. Did I do that right? Yeah. And then on the bottom, we get 4 minus 2 minus 2. So we get negative 10 over 0. So that tells me that there is a vertical asymptote at -2. So we're coming in from the left. So what is a value like 100th away on the left side of -2? What do we want to plug in for this one, would you say? That's to the right of it, if we think about negatives. So what's to the left of -2? Negative 2 point, let's go 0, 1. Let's go 2 decimal places. Okay. If you get a positive value, you're going to positive infinity. If you get a negative value, you're going to negative infinity. Number 105 is probably the same. We're approaching a vertical asymptote. What is to the left of 1?
0.9.
Yeah, so let's go 0.9 or 0.09 or 0.9 or 0.99. Let's go 0.9. Let's see. Oh, 107, 109, and 111. I like these ones. They've given you 3 facts up above. As we approach 6 for F, we're getting to a height of 4. As we approach G, we're going to a height of 9. As we approach 6 on H, we're getting to a height of 6. So all we're doing is using the limit laws to evaluate. So this is really just 2 times the limit as we approach 6 of F times the limit as we approach 6 of G. So it's just going to be 2 times 4 times 9. You just use them. I mean, because they've done the work for you, and that's as easy as it is. So it's just, yeah, because they're just like so straightforward and nice. They're just, if they give you the values, use them to evaluate. So it's pretty straightforward there. Okay, now let's jump to 115. 115 is a piecewise function. It says use a calculator to draw them. You draw them by hand. There's where I'm different. Please draw them by hand. You can use a calculator to check it, but I want you to graph the piecewise function and then answer the question. What's to the left of 3? What's to the right of 3? So for this one, you have to use the top function. For this one, you have to use the greater than function. Okay. So that's 115 and 117. 119, you're using the graphs shown. Let's do 119. Okay, so we have an f function and we have a g function. We are approaching -3 from the left. Okay, so let's go up to the f function. As we approach -3 from the left, we are getting to a height of 0. So where the f function is, that's 0. For the g function, as we approach -3 from the left, we are a height of -2. So that's just going to be 0 minus 3 times -2. They're almost as easy as the one before. If you have the graph, you can just find the limits and substitute in. So that's how you do those ones, and that's it. Okay. So for the rest of class, just work on these, and then tomorrow we'll see where we head for there. We'll probably start 2.4.